Hello everybody, I hope you can hear me. I think hello Roman, I see your text there. Um, okay, is, uh, this is the third webinar. This is we're going to talk about convolutional neural networks. I'm going to switch to screen sharing so you can see what we're talking about in a minute. But first, I want to give a brief overview of the things that I have time to talk in this short webinar. So the first thing I want to touch base on is image data and its properties. This is something that is always overlooked when people start talking about CNNs, and is assumed that you are familiar with why are we going to use CNNs instead of multi-layer perceptron like we use for the bike sharing project. And I think that is interesting to touch base on that. And later we'll go briefly over the process of feature extraction, and just you have seen the classes on convolutional neural networks, so I won't go into all the details, but I want to skip through what is a hierarchical feature extraction process, and why CNNs are good for extracting hierarchical features. And then I want to give you I just want to interest you in the project at hand. So what is the requirements, what is the rubric, and maybe just show you a little bit of how does the result project looks like, so we can take a look at my older project and just get an idea of where you want to get. So okay, with that in mind. Oh yeah, I always also want to start with a brief presentation of myself. So as you know, my name is Adrian Sarno. I have here a few bullets about myself. So I have a background in computer science. I have a BSc in computer science from University of Buenos Aires in Argentina, and a master's in computer science from Trinity College Dublin in Ireland. I work in Microsoft for more than 50 years, I'm afraid to say, and then transitioned into data science 3 or 4 years ago. And I took the Udacity machine learning nano degree, the deep learning nano degree, and the AI nano degree. So all those classes give me a little bit of wide spectrum background in the historical machine learning and the new stuff that is the deep learning, which I use at work. Currently, I am a data scientist at patternx.ai. It's an AI company dedicated to cybersecurity products, and basically I design models for detection of cybersecurity intrusion, and one of the models that we use is based on CNNs. Is a CNN for detecting. It's a classifier for phishing domains. So it's based on character-based CNN for character-based NLP. And there are other areas of cybersecurity where CNNs are used, like ideally, usually in virus detection. All the antiviruses today, they use CNNs. They are preferred because they can recognize hierarchical features inside the program or inside the essentially anything that runs is a process, and it has a hierarchical structure. So CNNs are very good to scan that. This is mostly done by other companies like antivirus and firewall companies. And I also work on LSTMs, some sequence models. So we're going to see sequence models later in this course. But basically I do an LSTM for detecting script obfuscation. And the rest of the cybersecurity models are more like traditional machine learning models, because the data is more like the bike sharing project, where you just have a table of numbers. So you can consider that the features have already been extracted there. You just have the numbers. There is no need for a deep learning model. Although we did use a deep learning model for the bike sharing project, I think that you could have actually also do it with a traditional machine learning model, like something as simple as linear regression, because the data was already in columnar format. So the features have already been extracted. I actually recommend you to try. If you have resolved the project, you can see if it works with, let's say you reduce the number of neurons in the hidden layer to 1, and therefore you will have a linear regression essentially, and well, maybe non-linear, but it's only 1, so it's pretty much like a simple traditional model, and you'll see that still works. So might require a little bit more of training epochs, and that is because the type of data that you had in that project is it doesn't require the kind of hierarchical feature extraction that deep learning does. And with that, I'm going to move into the content of this talk. So, okay, this is my projection software that is getting underway. And where is the present here? Okay, all right. So these are my slides. I'm going to share them later because they have some links at the bottom. So so this is what I've been talking about. We're going to go over that. This is the first thing that I wanted to talk about. So image data. What's special about image data? And why all the machine learning models have been so, the deep learning models have been so successful with image data. So if you think of how the dog project data differs from the bike sharing project, you remember that in bike sharing project you just have a data frame with numbers in columns, or they could be categorical features, but essentially it was all divided in columns, and each column has different semantics. Essentially, it's a different thing. So in images, things are a little bit different, because we don't have columns and rows. We actually have a matrix, right? But each one of those points in that matrix is homogeneous in terms of series coming up here. I don't know why. Sorry. So it's homogeneous in the sense that every point in your data, in your input data, has to be interpreted exactly the same as a pixel. Is a pixel, right? While in the bike sharing data set, every column could be interpreted as something different. One was a date, the other one was I don't remember, but it was a different thing, right? It was the weather or things like that. So you wouldn't actually bag them together and do some weighted zoom between them, you would actually treat them different. So in the case of images, because every point is a pixel, you could hierarchically compound them, and after a few hierarchical compositions, you arrive to a number. So and that's what we call feature extraction. Another property of the image data is that it has 3 dimensions. So it's a stack of 3 2-dimensional pictures. So a green picture, a red picture, blue picture. So if you think about that, in each picture, the pixels are related to their neighbors, right? So basically, most pixels, they are either sitting on an edge or they belong to an object. So they are inside the dog or outside the dog, or they are in the edge. So the locality, the local area of the pixel, it matters. That is where our analysis is going to go. But there is no locality analysis on the depth of this tensor, this 3-dimensional tensor, because the depth is just a stack of different colors. So you don't really, have a distance there. I mean, the red or the blue or the red of the we are not analyzing the distance there. So hello, this is Adrian. I'm starting the webinar again because it looks like we have some streaming problems the first time we tried. I'm going to switch directly to the presentation, which seems to be a lower bandwidth and it streams better. So here, and let me let everybody know that we're going to do it on YouTube. So starting again. Today we're going to see convolutional neural networks, and we're talking about a few aspects of convolutional neural networks that you might encounter a little bit confusing, and they're usually not developed in the coursework. So one of the main things that I want to talk about is why are they used and why are they so effective in image data, and what about the application of deep learning in data that's not image or text, like for example the data that we had for the bike sharing project. So I went already over my background. But I can do it again briefly. I work in a AI company for cybersecurity, and I design machine learning models for detection of intrusion in so behavioral patterns of users and devices in cybersecurity. We use neural networks and we use traditional machine learning, and that depends on the kind of data that we have to analyze. So we use a character-based CNNs for detection of phishing domains, and we also use sequence models like LSTMs for recognizing patterns of obfuscation in scripts, and we use many traditional machine learning models too. So today we're going to do, let me just switch into presentation. So I talked briefly about what is special about image data, and that makes it so suitable for deep learning, and what do we, all the lingo of feature extraction, what the different terms mean, and how multiple layers in a CNN mean a hierarchy of hierarchical features extraction, why having multiple layers allows you to extract features hierarchically. And I'll go into the details of the next project, the dog breed classifier. So how the data from the images in the dog project are different from the bike sharing project? Well, the images in the data in the images are pixels, so they are homogeneous in meaning. So every data that you receive when it comes from an image, you know what it is. It's a pixel. So what do you do with a pixel? It's just a number. Well, with a pixel, nothing, but with the relationships of this pixel with the neighborhood pixels, then yes, that's useful, because a pixel is either inside an object, like it's inside the dog, or it's outside, or it's in the border. And so looking at the differences of the values with the neighbors, you will be able to detect it if it detects the borders. And that is what we call like local analysis. This locality means that the proximity of the pixels is interesting. So we are switching from looking at the values themselves to looking at the relationships between the values that come in the input. And that is what we call locality. This analysis of relationships, local relationships, is not interesting to see the relationship between one pixel and the pixels that are far away in the image. Usually they are not in the same object, and there is nothing interesting to see there. So that's why we say that with the convolutional neural networks we analyze locality. Feature extraction is a term that we use in deep learning because essentially from the image we extract numbers that measure the probability of an object existing in the image. So extracting features is something that deep learning does automatically. So the way it goes in images is that we use an operation called convolution. It's something similar to scanning a time series with a window, if you have done it with a time window. In this case you use a space window, which is called a filter, and it's a square zone that you use to scan across the whole image. The operation, mathematical operation, is very simple. So your filter is just a matrix of numbers, small matrix like 5 by 5, for example, and what you do is element-wise multiplication with the numbers of 5 by 5 zone of the image. and then you do the weighted sum, and that gives you one single number, and that number is input to the next layer. So you can see how this process can be used to detect edges. In I think that we have already. Okay. Yeah. Well, this is one of the labs, Udacity labs, where we're going to input an image and see. We use something called a gray map, but essentially we just remove all the colors because they are not relevant for this. We just look at the intensity of the pixels, and the purpose of this is to use this. This is a filter. It's a 3x3 filter. There are two here, two different ones, and essentially what you're looking at is that excuse me. If we're going to detect borders, then we're going to multiply all the pixels on the left by negative numbers and the pixels on the right by positive numbers. In the middle, we are going to ignore them. And when we sum all this up, this is going to give you, usually, if you use this pixel over any part of the white image here, what's going to happen is that because the pixels of the image are have the same value on the left and on the right. See, this is just a white background. All the pixels have the same value. When you sum up, after multiplying element-wise, you sum up, you get 0. But whenever you have a border, like say these parents here, and you place these metrics exactly on the border. So all the black pixels are going to fall into the first column, and they're going to become some 0 because the blacks are 0. So there won't be any negatives, and the positive column, the positive column is going to multiply white numbers. White pixels over here. So the absolute sum of everything is going to be positive. So you are switching from 0. You have 0 here when you do the sum, to positive when you go over something vertical. And but it's not going to happen if you go over something horizontal, like this equal line. This equal line here. So see, this is the same, but to detect all horizontal borders. So that's how it works. It's called Sobel. Before deep learning was popular, all this was used to be engineered manually, and used to do the operations manually. So you didn't have an automatic process to learn these numbers. So researchers come with the numbers and say, okay, this is going to be useful. They do the convolution, but they didn't learn the filters. They themselves make this, engineer the filters. So with these filters, if you convolve it over the previous image, you see that it lights up in the borders. That means that the value is 0 here. Wherever you see black is a 0, and the white is because the filter to the positive value. So what you are seeing here is what we call the feature map, or the output of convolving the filter over the whole image. Here is the same with the other filter, the horizontal one. It actually detects the same borders, but you can see here a tiny little difference. You are seeing the border of the mountain, which is a horizontal line, which you don't see here at all. You don't see that line over there. Okay, so this is what's going to happen when you apply deep learning. You're going to apply tons of these ones you're going to get a lot of feature maps like that, and you're going to stack them up, stack the feature maps in a big. So that's going to give you the depth of the output. So your output of the convolution is going to have it's going to be a stack of feature maps like this. Okay, sorry. Okay, so feature learning is essentially learning the filters with gradient descent instead of hard coding them, like in the example that we just saw. Locality connected. Okay, locally connected nodes. Okay, well, yeah, at some point we talk about, in CNNs, we use locally connected nodes. What we mean is that the input of the layer 2, the input of the second layer, is the output of these convolutions, right? So each point that enters the second layer is a pixel in that black feature maps that you just saw, and is the result of applying the filter to the input image. And if you can see that that point that enters the second layer is only related to the 3x3 or 5x5 section of the input that was used for computing the convolution. So any node in the second layer is connected by this convolution, by this filter, to only a 5x5 area of the input node. It's not connected to the whole image, and that comes, and that basically is saying that yes, with this filter application, that we only analyze a local patch of the image, not the whole image. Sorry, this doesn't make complete sense. I'm just trying to put it together the best I can, but I think that it's important to try to capture that. So that's why I'm making an effort to explain it. Weight reuse. Weight reuse is another term that you will see thrown around in convolutional neural networks, and it simply means, okay, you see that filter that we are learning. We are learning those filters. This is a 5x5 matrix of weights. We call them weights, each value in that filter, and we are applying it to a lot of parts on the image, right? Because we essentially scan the image with that from the beginning to the end. So we are referring here to the fact that we reuse the same filter all over the image, and that is weight reuse. It means that we don't need a lot of weights to process the image. We see the same filter is used for the whole image, and then another filter and another filter. But this is understandable that this is a reuse, because we don't need a different filter to detect an object in one corner of the image or another. Is in the position of the object is not important as long as the filter detects it. So the next thing that we need to see is the hierarchy, the hierarchical way of detecting the image. So if you have seen that it's possible to detect edges with filters, so that would be what the layer 1 of the CNN will do. The second layer, it will have as input just the edges. So what can you do if you have as input a bunch of edges? Well, you figure out that a combination of edges makes a shape, right? 4 sides make a square, and a lot of lines, crosses, and can put together a texture. So you, in the second layer, you have filters that light up when they see combinations of the first layer filters that mean something important to essentially to the network that you're training. So that could be shapes, textures, and sorry, I don't have the output of the filters of the second layer here to show you, but there are plenty of those things around in the internet that you can look at. And in the third layer, and let me see, somebody in the channel needs. Okay, okay, thank you, Roman. I am in the third layer are you will probably already see parts of an object, and in the fourth layer you will see the object. You will see the filters light up when they detect the object. So excuse me. Once you are at that level that you have filters that give you positive values when they see an object, you can already apply the softmax, which is a function that allows you to classify things. So the softmax is essentially it takes a vector of values, like the output of the last convolution, and after that you can flatten it in a vector and then apply a softmax, and essentially it's going to give you a value that is close to 1 for only one of the elements of that output array. So this is the formula. It's an exponential function. So it takes a score, Zg, Z sub j is a score, is the output of the last layer. It could be negative or positive, but once you put it in an exponential function, you obtain a positive value. And with this formula, you convert it in a probability distribution. So essentially, you'll have as an output here a vector that has one element for each one of the output classes that you want. Essentially, if you want to distinguish between 10 different races, 10 different breeds of dogs, you can essentially have 10 values here, and each value will tell you the probability that the image corresponds to a dog of that particular breed. So and all the values are positives, and they add up to 1. So that's why we call it a distribution of probability. Okay, the last thing I want to show today is a little bit more details about the dog breed classifier. I want to get you interested in start looking at that and what is that we want to do here. So I have a link to the rubric here, but I probably better off just showing you my comments here. So in the rubric, they explain 6 steps that you have to complete. So essentially, the objective of the project is show you how in an actual production pipeline you have to piece together different models to do things, to do useful things. Normally, a single model may not do everything that you need. So in this case, for example, the inputs are pictures, and in those pictures there could be a human or there could be a dog. And this is very realistic, right? If you are going to put that on a website or somewhere, people upload an image, and you want to recognize whether there is a human there or there is a dog. And if there is a dog, you want to say, oh, I think that is a collie or whatever the breed that you recognize. But if there is a human, you don't want to say confuse it with a dog, right? So that would be funny in the best case. So that is the idea, to show you what can you use for that. So there is a model for detecting human faces that is called hard cascades. Is something that you can look up, and essentially it's not a deep learning model. This is just another type of machine learning model, and is used for recognizing human faces. But essentially it says, okay, this is a human face. No, it is not going to recognize the person. And it's very fast, and that's why it's used. And it's very easy to do the trade-off between performance and accuracy. So it's a good tool to use in production, where you have to deal with all those additional complications. Once you know whether it's a human or a dog, you can pass the image through one of the, basically to a convolutional neural network. And in this case, in the step 2, you shall see how there is a pre-trained neural network that you can use. That is the VGG16 is one of the neural networks that won the annual competition of object recognition, and a few years ago. But it's one of the networks that I still use for because it has been trained with a lot of images, and it recognizes I think that 1,000 different objects, and so you can use that to recognize dogs, and see how, without training or doing anything, you can just download one of these models, and like VGC16, and use it to say, okay, yeah, this is a dog. And it has certain limitations, of course, but in that step you see how you can use it without doing practically any effort. It's ready to be used. Then you can create a CNN yourself and train it with the images that you have downloaded from in this project. The rubric, it only asks you for a 10% accuracy, which means that, okay, just try to get it right 1 over every 10. And that is realistic, because with the amount of training and amount of data that we can afford in the project as a student, we are not going to train for days, and don't have enough data also. So the next one is to create the CNN using transfer learning, which means that you have to use most of the layers of the VGG16 network that have already been pre-trained to recognize edges and shapes and objects. The only thing that you have to do is to train the softmax at the end. To train the last layer and the softmax to be able to output all the different classes that you need for this project. So imagine that VCC 16 recognizes 1,000 objects. Among those objects, there are dog breeds, but there is also car and trains and all type of objects. So you don't want any of that. You just want to expand the number of dog breeds that your network recognizes. So you chop off the last part of the VCC 16. It means chop off. Just ignore that part. You pick up the output of the previous to last layer of the VCC 16 and input that output to your own classifier, which is probably a simple one-layer classifier with a softmax that tells you the probability distribution over the different dog breeds. And you train that final classifier with your images and your labels. And with that, you will get 60% accuracy. So it's amazing. You'll get it right 60% of the time, which is probably very close to human performance with this kind of problem. So essentially, step 5 and 6 are essentially the same. Is okay, once you have written your algorithm, that will detect a human, a dog, or other, or say, okay, well, this is neither. And just try to guess the dog breed close enough, and that's all the rubric is going to ask. And then finally test your algorithm with 6 images of the different classes and show what it comes out. Once you are done with this, because it's a application-oriented project, there are a few suggestions of how can you productize this. I mean, one of the things that you can do here is try to use data augmentation. So how to apply the it's a simple technique of data augmentation. Is usually used in when you are working with real data, and just starting to get familiar with that is useful. Another thing that could be useful is to turn your algorithm into a web app. So since you have put the effort in creating this project and playing with it, why just leave it there? When you move on to maybe do a job application, it would be nice to be able to refer to to give a URL and let people see how it actually works. If you can put it online, if you create a web app with Flask, it's a simple framework. You can put it there and run it in a in a cloud instance, and put it there for a few days. If you are applying for a job, let people connect, or you can show it on your phone even. And then there are other applications like overlay dog ears or things like that, which might take a little bit more work, but it's more like the kind of mobile applications that you see around, and people playing with that in videos and things. So functionality for dog mats, what it means here is when you have crossbreeds, you can say, okay, well, in this case, for this image, the softmax gave me 50% probability of this being, for example, a pug, 50% of being a beagle. And so you have a dog that is a mix of 2 different breeds. And then I don't remember what the last one is. Experiment with multiple dog and human detectors, but it's explained exercise. So let's take a look at, see if I can show you what one of these actually looks like. Okay, here is my notebook, and going over the same steps that we described. In the first step, you can see what they are asking for. So you insert the data and just show different statistics here. So there is 133 total dog categories, 8,000 dog images. So this is no application of your model. This is just counting the input, right? Yes. So the first step is to detect humans, and when you apply this package, OpenCV, import it as CV2 and apply the cascade classifier. So OpenCV already has the method to apply the cascade models, and the hard cascades are essentially models that are already trained. So all you have to do is load it up. So we want, in this case, just that you to learn how to use those models. Here is, for example, how the model works. It gives you these 4 points around a face. So then you, when you want to detect dogs, you have okay, here is a different model, ResNet. ResNet 50 is one of those pre-trained models. You can load it and apply it as a dog detector. You just have to know which ones are the categories that are dogs. So if the prediction is between these two numbers, it means that you are within the categories that correspond to dogs. So you can count this as a dog. And you will need to do some data pre-processing. So we usually, the value of the pixels is from 0 to 255, so you have to normalize it. We want numbers between 0 and 1. And then here you have when you want to train a CNN from scratch. So I think this is what is asking you to do. So you have convolution, max pooling, convolution, max pooling, and essentially, finally, global average pooling. Find out a little bit more about this one, and then you apply. Finally, it always ends with a dense layer, and then you apply the softmax. So here's a network. Here's the output, and okay. I think that this network, if I'm not, yeah, this is built with Keras. Is not PyTorch. It's a previous generation framework, if you want. But the APIs, I mean, these functions over here, they are all very similar in all the deep learning frameworks. So it's going to look very similar in your case. So here is a little bit of what you do for data augmentation. There is a generation of the image. that given the input images, it does different things to it, like for example, randomly shift the images horizontally, or vertically, or flip them. You can do different things with the images, and you obtain another data point for the same category. So that's a way to augment your data. And then you should train it and get a little bit better accuracy, that's all. So here is the training process with the augmented data. So here's your test accuracy, 4.6%. Not very impressive, but that's that goes to show that, you know, with a small number of images, is very hard to get a good result, and that's why we use transfer learning. So transfer learning is you get a CNN that has been trained maybe for another purpose, right? Maybe for detecting other categories, but you have to recognize that in the process of visual sensing, the most of the work is done at recognizing edges and small patterns, and you can reuse that from another CNN. That it doesn't need to be different for your CNN, as long as you're looking at images. So half of the work is already done. All you have to do is now that you have something that recognizes borders and textures and shapes, you need to learn combinations that map into the categories that you are interested. So so yes, you see we're obtaining better and better accuracy, and here is when we really start with transfer learning. I'm going to skip to the end just to show you that the accuracy now is much better, because you are using all those low-level filters that have been trained with a lot of data. This is just a little bit of logic. So when they say implement your algorithm, what it means is, okay, let's see. You get an image, and then you run it through the face detector, and if it tells you that it's a face, categorize it, otherwise it's none, and depending on the category, you can pass it to the through your function to recognize the breed, that kind of things. So here you can call it with 6 images. It asks you at the list. So and here is one that it looks like a mix.